am just up here briefly to introduce David Lopez. David Lopez, well, Rafa mentioned something about new technology. You want to talk about new technology, it's this guy right here. Really amazing. He is not only offshoring, but can I say off-worlding? It's pretty fantastic. He has 15 years of experience in operational and financial modeling. David works at Outpost, which basically develops satellite equipment that is good for the environment. So it's very forward-thinking and something you've probably not heard about before. I'm just really, really proud to introduce David. He has 2 TED Talks. He's really an expert at what he does, and he's inspiring to me.
Thank you. Hope everybody's enjoying their lunch. I'm going to get back to this in a minute, but I need to do this first. That's about right. All right. The space economy. It makes us wonder. It makes us learn and unlearn. It is so infinite in its resources, and space is vast, mysterious, and unexplored. Most of the people in this room have heard about it or read about it. Some of you are amazed, intrigued by it. And yet just a few of the people in this room participate in the space economy. Now, why is that? My guess is that for the most part, the companies you work with, your clients, are not in space yet. But why would we need to wait for them to take us to space? My mission today is to create a spark, to spin your wheels, to ignite your engines, to add that last bit of information to launch your curiosity into space. And in doing so, I hope I'll entertain you as well. Now, you don't need to be Elon Musk or a tech billionaire or an eccentric scientist. Now, some of you might be thinking this is redundant, but my point is that space is not all rocket science. And there is a lot more to a rocket than just science. And at the end of the day, every new industry needs a best-in-class accountant, a passionate, outspoken leader, and a darn good attorney. So, without further ado, counselors, let's look at the evidence. I'm calling this speech, this talk, Space Shoring in Leo. We're going to talk about it in a second. And we're going to talk about what the next best thing is, which is manufacturing in space. It's actually happening today. So in order to get there, I'm going to structure this talk in 3 parts. The first part will be the science. The second part will be the businesses. And then the third part will be relevant for all of you, will be how can attorneys, lawmakers, and professionals of the law can participate in the space economy. And I'll give you the when, the what, and the where. So, let's see. Cool. So this is basically the outline. I'm going to add perspective first before we speak about the science of Leo. I'm going to tell you, Leo is not a person. It's the acronym for low Earth orbit, which is an area of space that's really close to us. That's where most of our satellites are. And then I'll add more perspective, you guys can see here, Like a lot of perspective is going to happen today. So hopefully I'll get you ignited into joining the space industry. Here we go. So the first time I read about the space economy, I read about this asteroid. It's 16 Psyche. It's an asteroid that is orbiting Earth in a way, but it's orbiting the sun. It's located in the main asteroid belt between Mars and Jupiter. And the first time I thought about it is like, obviously we want to mine this. After all, it's estimated that this asteroid is worth $10 quintillion. That is the equivalent of 100,000 times the global economy. So it is so rich in iron and nickel that we literally do not have enough money in the world to buy like even a part of this. So this clearly opens up the why aren't we exploring this? If there's so many resources, maybe we can figure it out. Now, it is very far away. It'll be the equivalent of a galactic offshoring, not space shoring. So, or space nearshoring, what I'm calling space shoring. Now, just imagine that number, right? If you're into marketing, usually if you have a commodity like iron and nickel, if you have 1% of the market, you're golden, right? You're going to be awarded, you're going to be well known in the market. You only need 0.001% of the market share of this asteroid to make your net worth $100 trillion, which is our current GDP as a world, as a planet. So if any of you, it's not that ambitious, but you still want to be rich, this is it. This is the way to do it. Now we're going to talk about the science of LEO. LEO stands for low Earth orbit. It is 100 miles away from where we are right now. But instead of looking across, we need to start looking up. This is closer than Mexico is to us right now, but going vertically. This is where most of our cellular satellites are. This is where all our images, all the likes, the shares, the tweets happen. I cannot talk about LEO without talking about MEO and GEO. MEO is the orbit where all GPS satellites are located. It's a little further down the road, and it has its reason for being there. It covers more area, but they move slower. And then finally, GEO is where we have our internet satellites, like satellite internet and SAT TV as well. So this stands for mid-Earth orbit, and this stands for geosynchronous Earth orbit, which is basically we can place satellites here so that when we look at them from Earth, they're static. They never move because they're orbiting around Earth at the same rate that we're spinning, right? So it's always going to be staying in the same point. Now, the relevance of what we're talking today, we're talking about nearshoring. I'm going to bring up the word space shoring now. And I want to put things into perspective. Now we're going to talk about the science. In order for any object to orbit around any planet or any other celestial body, they have to be going really, really, really fast. Our crown jewel is the X-15. It's a plane that can reach speeds of up to 4,500 miles per hour. That's 7,200 kilometers per hour. This is faster than any bullet that's ever existed in humanity. Like the fastest bullet goes at 3,200 miles per hour. Now you want to know what goes faster than this airplane? A satellite, and it's not as sophisticated. It just needs to be going at the right direction. Now, at the right speed, and orbiting in the right place. So how did this work? The speed of a satellite is 17,500 miles per hour. That's about 28,000 kilometers per hour. It's going that so fast that it makes a lap around the Earth in 90 minutes. That's shorter than some people's commute here in Texas. Well, it used to be mine when I lived in Houston. So that's the time it takes a satellite in LEO to go around Earth. So I'm going to go into a little bit. This is going to be a flashback to school days, I hope. And I'm going to talk about what happens with these speeds, right? We have this big arrow pointing to the right, right? That's usually how we represent velocity. But thanks to calculus and physics, we can break it down into smaller arrows that are going exactly at the same speed, but we just want to separate them and, make them add up to this big arrow. So whenever a body is traveling in the vacuum of space, it's just going at a constant speed. Whenever it doesn't find any orbits or any gravity to pull it and deflect it from its current path. So it'll look something like this, right? This is a shorter arrow, and it'll continue going. I'm putting into a darker line the trajectory. And then, we have the equivalent of that big arrow representing velocity. We just broke it down into smaller arrows. Now, if we add, and this is the fun part, if we add our home to this equation, there will be a moment where the force of gravity, or the way Earth warps the fabric of the universe, which is, I think, the physical definition of gravity, will deflect its course. So instead of going straight, it'll just change its path just enough so that instead of going into those ghost paths that I drew there, it's going to continue falling into the same effect. And again, it'll go down instead of going to the right place. It'll continue to be pulled to Earth. And if you guys can see, this arrow is always trying to escape Earth. But then gravity pulls it back in, and it's kind of correcting its course and correcting it and correcting it. And that's what keeps it spinning around Earth, orbiting around Earth, right? So this will continue forever unless the speed of this satellite is faster and it just gets ejected out of orbit, or slower, where the force of gravity will start pulling it and dragging it into the atmosphere, so that at some point the atmosphere will slow it down enough to make it back to Earth. Now, I want you guys to focus on this one. This was Isaac Newton's thought experiment. He thought that if you put a cannon at the top of the highest mountain on Earth, and you fire that cannonball at about 8 kilometers per hour, that cannon will hit him in the back of his head. Why? Because if you go slower, it will happen what we all see happen in a cannon. It just falls onto Earth. If it goes a little faster, it reaches a further target. But if it goes at exactly 8 kilometers per second, the speed at which this cannonball will fall will be the same as the curvature of Earth is getting away from it. So for every 8 kilometers, Earth drops 5 meters. But by then, the cannonball is 5 meters away from Earth again. It'll continue to go into this free fall state until the end of time. Now, you guys want to see how many of these we have around Earth? This is being tracked by the US Space Force. This big ring is, if you guys remember, GEO. That's where we have our internet satellites and TV satellites. We're going to get closer into MEO, where the GPS satellites are. And then all those little ants that you see close to Earth are in LEO. 95% of these are debris. So it makes you wonder. I see some people spinning their wheels. Who's managing this? Who regulates who gets out of space? Try leaving Earth with this situation. This is LA traffic to the power of, of satellites. Here we go, exactly. Now, the size of these satellites, they're not to scale in order to make them visible. Some of them are as big as a bolt. Some of them are as big as a school bus. So it is an issue that requires regulation. Sometimes it's traffic regulation, but it also refers to regulation in terms of who goes first if we get to the line at the same time and we want to leave Earth. Right? Who has the right of way, so to speak. So with this is going to be more familiar for a second. Nearshoring is, I think we can all agree, it's a business strategy that increases the efficiency of companies by facilitating the supply chain process, right? And it has three ingredients. The first one, nearshoring happens in a nearby country to facilitate the supply chain process. It happens at a similar time zone to facilitate coordination. And finally, it provides better unit economics and makes investors happy. What I'm proposing here, it's just a slight variation of this, to call it space shoring, just for today. And then we can all agree it's going to be nearby. It's going to be closer than some of the nearshoring countries we work with. Time zone will be no time zone, or all time zones, if you want to see it that way. And then finally, the better unit economics, that's the meat of this talk. You're going to see that they can be exponentially higher. And I'm not using the word exponentially loosely, given that this is kind of like a science talk. So, the business of Leo. You guys all, you already eat, right? You're good. Okay, I'm going to ask the audience to please stand up for a minute. Stretch your legs just for 1 minute. And I want you to focus on your legs. Your legs right now are engaged, right? You're contracting your muscles. And the degree at which your muscles are engaged has to do a lot with the gravity that we have here on Earth. You may sit down. Thank you. In 1969, we went to the moon. Neil Armstrong, Buzz Aldrin, and Michael Collins had to follow a 15 to 30-minute daily exercise routine. Why? Because in space, you lose up to 20% of your muscle mass in just 5 days. Today, that exercise routine has been extended to 2 hours. Why? Because they want to keep astronauts longer in space. Sounds like astronauts could use a good syndicate attorney. But muscle atrophy, skeletal atrophy, is not the only thing that happens in space with our body. Our bone density reduces and our immune system gets compromised. We're more prone to get diseases. Now, these are signs of aging. So, in a way, to us humans, space is an accelerator of death. But at the same time, in being so, it is, or it can be, a guardian for life. Because it becomes a fast-forwarding machine of life, and as soon as we come back to Earth, everything gets back to normal, for the most part. But if you have the experiment of identical twins, one goes to space for about 3 weeks. The other one stays here on Earth. And you compare the way their protein, like their myocytes, which are the building blocks of protein, are breaking down in space and having a perfect control back on Earth. You can compare the differences at that level and maybe start understanding a little better of what happens when we age. Maybe start finding solutions to certain age-driven illnesses. So it becomes an issue of just trying, right? Just have a control here on Earth and take somebody to space. They're going to be perfectly safe. They'll lose bone density, they'll lose some muscle, their immune system might be compromised. But we can have A/B testing at a human level without being unethical. It's just, I guess, voluntarily. All right, so this is the biotech portion of it. There are a lot of nuances to it, but in general, I want you guys to focus on how gravity engages our muscles here and how they are not engaged in space. Now, the next part, and this is, some of you are wondering what I did in the beginning. I wanted to make a small exercise with all of you, where we're a company that produces gummy bears for kids, but they have vitamins in them. So I have recreated the gummy bear mix and the vitamins at the bottom. If you guys remember in the beginning, I kind of stir this up quite a bit, but all the vitamins kind of like went to the bottom of this container. This is not a magic trick, by the way. So if I'm ready to pour this, let's imagine that each of these glasses is a gummy bear mold. Let's hope I can get this. So as you can see, I'm not very good at distributing drinks in a jar, but the other part is you're going to notice that this gummy bear is full of vitamins. And these gummy bears, well, they're going to just be delicious. Right? They're not distributed the same way. And why is that? Because the vitamins that I stirred in this mix went to the bottom of the container, making it really hard for us to equally distribute the vitamins across these 4 gummy bears. This doesn't happen in space. Like if I had stirred this in space in a sealed container, the distribution will be even, homogeneous, and perfect. Now, I'm not proposing we do this with gummy bears, but there are drugs that save lives that are very, very hard to get the right amount into a small little pill. And we have some workarounds, right? We stir the mix before we pour it. We have larger containers to distribute the key ingredient more evenly. But at the end of the day, they're just workarounds. If the numbers are right financially, you can manufacture this in space. And even though it might cost you 10 times, 20 times, 100 times, your yield could be 100 million times better. So the unit economics could be there. It's just a matter of running the numbers. But again, I'm pointing out the gravity aspect on manufacturing that we're facing today is key for producing better unit economics. And again, it's near us, sometimes closer than our nearshoring partners. And we can basically contact these satellites at any time of the day. Now I'm going to talk about Z-Blend. Well, Z-Blend is it's a glass that was set to replace silica glass, which is the one we use for optic fiber cables, the ones we use for internet. The thing with optic fiber cables is that we need repeaters. Similarly, similar to what we do in our homes sometimes with the internet. We just put a router on the second floor so that it can spread the signal a little further. Now, C-blend was a great promise because on paper, you didn't need that amount of repeaters in order to extend the signal of internet. However, when you manufacture it on Earth, it looks like this. You can see those kind of like crystallized, this is C-blend being poured a little better than I did with gummy bears, but it's being poured into a container, and you can see all these crystals forming or formed after C-blend has been manufactured. And this is what C-blend looks when it's manufactured in space. So this level of purity allows to reduce the number of repeaters, the ones we were talking about, a factor of 40 to 60, making it economically much, much, much viable than using either silica glass or the Z-blend made in Earth. And just to finalize, this is the fourth business case. I'm going to talk about semiconductors. The thing with semiconductors, I don't know if this will run because I don't have a connection to the internet, but these are particles of dust that are settling. One of the most expensive costs of a semiconductor fab is to keep the clean room clean. Now, the clean room, for you that are wondering, like, what's the right standard? A clean room has 3,500 parts per million in a cubic foot of little particles. It could be dust specks. In any part of the street, that same cubic foot has 35 million particles of the same size in microns. So this is a very, very, very clean room. And one of the big issues is the fact that gravity pulls these dust particles into the semiconductor substance, the one that we finally use to assemble into our computers. Now you guys want to wonder or want to guess what happens in space with this dust? It does not settle. No settlement, which are two scary words, I know, for attorneys. But the fact that we could have semiconductor factories in orbit with the robots that are already making these semiconductors on Earth could make it worthwhile to just have them be produced there. And then, a lot of efficiency will be achieved. All right. Sorry. It could be human hair, tissue. It could be particles coming from. Correct. Yes. There's also chemicals. When you produce semiconductors, there's gases that are being produced in the process, and then they can contaminate the next part of the process. They're just there. So having exhaust fans is a big thing. If you have those same, processes in space, you can isolate the manufacturing process in compartments, basically. All right, so let me see if I can do this. This is the part that I think it's important for everybody to at least have the perspective on how science has moved us so quickly into where we are right now. So in order to do that, I'm going to put things into perspective again. And I'm going to compress the history of us, the modern man, Homo sapiens sapiens, into a 24-hour period. And then I want you to see when during that day we discovered certain things and what happened next. So let's see how this looks. Hopefully there's going to be sound. If not, we'll make it work. Okay. All right. So this is roughly 300,000 years ago. 0 hours, 0 minutes, and 0 seconds. At 7 p.m., 51 minutes and 57 seconds, we moved out of Africa. This is all compressed in one day, right? So we went into Europe, we went into Asia, because it was too warm. We didn't want to be eaten by our natural predators. We were escaping droughts too. And from Asia, using canoes, we went into Australia. And during the Ice Age, we went into North America through the Bering Strait. At 10 p.m., 53 minutes and 8 seconds, we invented agriculture by seeing the way the world moves and the seasons. And through storytelling from our ancestors, we understood which crops were better for us, which ones were easier for us to grow. And in doing so, we started settling. At 11 p.m., 26 minutes and 30 seconds, we started keeping track of time. The Egyptians divided the day in 12 sections of 2 hours each. Together with agriculture, we started becoming better at dividing the day, knowing when to sleep, knowing when to hunt, knowing when to gather. At 11 p.m., this is the same day, by the way. I'm not going throughout different days of the week. 11 p.m., 34 minutes and 37 seconds, we invented the wheel using logs. We started moving bigger rocks, creating forts, protecting ourselves. 11 p.m., 46 minutes, 32 seconds, we invented the alphabet. The Greeks invent the 30-letter alphabet that includes both vowels and consonants. This is 13 minutes and a bit before right now, by the way. At 11 p.m., 52 minutes and 37 seconds, the Middle Ages begin. It's a period of time where some development occurred, but then also a lot of superstition, a lot of fear. The Black Plague happened. People didn't know what it was about. Some of them thought it was the gods. Some of them thought it was penitence. And it was a period of time of great despair. And it's also a period of time where we were further away from science, from having certain degree of methodologies around the phenomenon that happened on Earth. And then at 11 p.m., 57 minutes and 16 seconds, we were born again. The Renaissance. Christopher Columbus makes his famous or infamous discovery of America. Magellan makes the first trip around the Earth. Gutenberg creates the press, and books start being printed, translated, and exported. People become curious about other cultures. They start reading stories about faraway lands where there's kings and there's other spices. The Mona Lisa and the Sistine Chapel were painted in this period. At 11 p.m., 58 minutes, 44 seconds, the Industrial Revolution begins. This is, again, 1 minute away from where we are right now. We cure cholera and malaria. And sorry, smallpox, not malaria. Um, we start producing pharmaceuticals at a level that protects human beings. We take 20% of the European population out of poverty. Railroads start connecting cities. People start being communicated through letters, through commerce, through communication. And then at 11 p.m., 59 minutes and 25 seconds, that's 35 seconds ago, Wilbur and Orville Wright make the first successful human flight possible. It took them 4 years of research and development, at least that's how we know it today, to do a 12-second flight. 4 years for 12 seconds. That was enough because only 19 seconds after that, we took the man to the moon. It took 66 years from a very precarious airplane to having the technology to get out of our orbit and make it to space. At 11 p.m., 59 minutes and 53 seconds, SpaceX is founded, making space accessible for most of the world, if we're talking about countries. At 11 p.m., 59 minutes and 56 seconds, space became the new frontier. And now, today, you'll understand what I call the next best thing. And so many of you are wondering, what can we do to join the space craze after this perspective that I brought? I hope that some wheels have started to turn. So I'm using this beautiful picture from SpaceX. It's showing a rocket being launched to show you in this very picture the different ways where attorneys, lawmakers, and any professional of the law can help. And I'm showing this first bit a little outside of the launch pad because, as you guys probably understand, there's a lot of coordination before a launch takes place. Usually it happens at least a year ahead of a launch. So how can you help? Well, there's a lot of help that is needed by startups, by big companies, and even non-space companies that just want to go and test their products in space. So corporate law, a lot of contract work, a lot of companies want to get to space, but they don't understand the way they can go through the paperwork that NASA requires. I'm putting it lightly. Contract law, there's a lot of contracting happening with the DoD, the Department of Defense, US Space Force. Companies that have great ideas don't always know what the laws look like. They don't know how to put together a contract that covers their bases. In terms of IP, intellectual property, you guys can imagine this is on its own a whole economy. It's a whole industry, just space IP. The licensing around it, the permitting, insurance law, it's going to be big. Insurance, not just of the rocket, but also of payloads that are coming from space after doing tests, after doing manufacturing. Environmental law with the EPA. As you guys can imagine, there's regulation around how much contamination happens when a rocket leaves Earth. And that needs to be addressed. The next section is more regulation. So we have NASA, we have the FAA, the US Space Force, ITAR, and the FCC, all of which require assessments. They require the right legal framework to be understood, and clients of yours could very well benefit from having somebody that raises the flag and says, you can't do that, but you can do this. Again, at this stage, most of it is related to regulation. The next slide makes me laugh a little bit, but I'm sure you guys have some clients that make you want to be in that rocket. International treaties. Whenever we go to the moon, there's treaties that have been signed by the space powers. India just got a successful launch into the moon. Mining laws and rights related to mining asteroids, mining the moon, if something interesting is found. Space tax and regulation, who's going to address all the traffic in space? Is there going to be a space tax that everybody has to pay for in order to benefit from getting a faster internet? And insurance law, again, insurance has several tranches. And if you successfully get to space, then you cross over a tranche. If you do that enough times, insurance can really, really grow really fast, just based on successful launches. And then on the way back, we have trade law, customs. If we're sending something, let's say from the US through space, and our client is in Japan, it has to go through customs. Now, which customs should it go through? Is it the US or is it Japan's? And that's a conversation that obviously creates, again, a wide variety of alternatives. And this one, once we get out of the launch pad, contract law, re-signing documents. A lot of the space industry is based on milestones. So if you bring something back, that opens up a new level of contracting with the government, a new level of service, a new level of volumes that you can purchase, etc. So this kind of is a big picture of the things space law can do for a lot of companies. And these are my suggestions of good resources that I use every day. The book, it's right here. This is one of the books. I didn't write it. Payload is a great newsletter, payloadspace.com. You get an email every day with high-level details of what's happening in the industry. And then Cosmos Economy. I haven't read that book, but it's on my Amazon cart. It's been recommended to me. Now we're getting to the end of our journey. I think I'm a little 5 minutes over, I think. We're fine? Okay. And I hope I created that spark. I ignited that curiosity because you guys represent a lot for smaller companies that don't have the resources, the knowledge, or the framework of law, that want to be in space. And I hope that you want to join the space economy, not by being dragged by your clients into space, but by taking your clients to space. Now, that's a law firm, right? That's the law firm you want to be. And the reasons, they can vary. You want to make money, great. You want to make the world a better place, that's also great. If you're a bit like me, it's a little bit of both. But at the end of the day, independently of the reasons, the philosophy, the religion, or the race, rest assured, there's space for everyone. Thank you.